Most people think they know Detroit diesel engines. You've heard the stories about the Screamin' Jimmy, maybe even worked on one yourself. But what you didn't know is that the 8V92 holds secrets that even seasoned mechanics have never discovered. In the next few minutes, you'll discover 20 shocking facts about this legendary power plant that will completely change how you see Detroit's most misunderstood engine, including one that involves a mathematical impossibility that somehow worked perfectly. The 8V92 was named after simple math that nobody believes. Here's something that blows people's minds when they first hear it. The Detroit 8V92 gets its name from the most literal math possible. 8 cylinders times 92 cubic inches per cylinder equals 736 cubic inches total. That's about 12.1 liters for those keeping track. But here's the kicker. When Detroit engineers first proposed this naming system, the marketing department thought they were joking. No engine company had ever been that straightforward with their naming. Ford had their Windsor and Cleveland engines, Chevy had their small blocks and big blocks, but Detroit just said, here's the math, deal with it. The 92 series followed this pattern across the board. A 6V92 had 6 cylinders at 92 cubic inches each. A 12V92 had 12 cylinders. A 16V92 had 16. It was so simple that mechanics initially thought there had to be more to it. There wasn't. Detroit's engineers were just that practical. They figured if you're going to work on these engines, you should know exactly what you're dealing with from the name alone. No fancy marketing names, no mysterious codes, just pure mechanical honesty. And that straightforward approach would become a hallmark of everything about the 8V92. It breathes backwards compared to every other diesel. The 8V92 uses a 2-stroke Uniflow design that completely flips conventional diesel thinking on its head. While 4-stroke diesels breathe in through valves and out through valves, the Detroit does something wild. It breathes in through ports in the cylinder walls and out through 4 exhaust valves per cylinder. This means the engine literally can't run without a roots blower. Not for power, not for efficiency, for basic survival. That blower isn't optional like a turbocharger. It's the engine's lungs. Without it pushing air through those intake ports, the 8V92 becomes a 736 cubic inch paperweight. The Uniflow design creates a one-way air path through the engine. Fresh air enters at the bottom of the cylinder through ports that the piston uncovers. Exhaust leaves through the top via conventional poppet valves. This creates a scavenging effect that pushes out all the burnt gases while filling the cylinder with fresh air. It's like having a constant breeze blowing through your engine. The turbocharger, when fitted, only adds boost pressure on top of what the blower provides. The blower handles the breathing, the turbo handles the power. This dual charge setup gave the 8V92 incredible power density for its time. But it also meant you had 2 devices spinning at high speed, which leads us to why these engines sound like nothing else on Earth. The Screamin' Jimmy nickname came from physics, not power. That famous Screamin' Jimmy nickname didn't come from the 8V92's power output. It came from pure physics and the human ear's response to certain frequencies. These engines typically govern between 1950 and 2100 RPM, which is screaming fast for a diesel. But here's what really created that signature sound. The combination of a roots blower spinning at twice engine speed and the rapid-fire exhaust pulses of a 2-stroke created a harmonic resonance that hit exactly the frequency range that human ears find most penetrating. The blower alone on an 8V92 at 2000 RPM is spinning at 4000 RPM. That creates a whine that cuts through any amount of engine noise. Add in the fact that a 2-stroke fires every revolution instead of every other revolution like a 4-stroke, and you get twice as many power pulses. An 8V92 at 2000 RPM produces 16,000 power pulses per minute. That's 267 explosions per second. Your ears interpret this as a constant high-pitched scream rather than individual firing events. Detroit actually tried to muffle this sound in later versions for civilian applications. They added resonators, changed blower designs, and even experimented with different exhaust configurations. Nothing worked. The Screamin' Jimmy was going to scream no matter what you did to it. Fire departments actually loved this because you could hear their trucks coming from miles away. Bus passengers, not so much. It has a square engine design that shouldn't work. The 8V92 uses what engineers call a square-ish design, with a bore of 4.84 inches and a stroke of 5 inches. This near-square configuration goes against everything diesel engineers typically believe in. Conventional wisdom says diesels need long strokes for torque. The longer the stroke, the more leverage on the crankshaft, the more torque you make. But Detroit threw that rule book out the window. They made the bore and stroke nearly equal, which should have resulted in a high-revving, low-torque screamer. Instead, the 8V92 pumped out around 1,250 pound-feet of torque at just 1,300 RPM. How did they pull this off? The secret was in the two-stroke design. Since the engine fires twice as often as a four-stroke, it makes up for the shorter stroke with sheer frequency of power pulses. It's like comparing a sledgehammer to a jackhammer. The sledgehammer, long-stroke four-stroke, hits harder but less often. The jackhammer, square-ish two-stroke, hits lighter but much more frequently. The end result is the same amount of work done. This square design also allowed Detroit to keep the engine compact. A longer stroke would have made the engine taller, which was a problem in many applications. This 8V92 needed to fit in buses, fire trucks, and marine engine rooms where height was limited. By keeping the bore and stroke nearly equal, Detroit created an engine that was powerful, compact, and defied conventional diesel design theory all at once. The wet liner design let you rebuild it with basic tools. The 8V92 introduced wet cylinder liners that revolutionized field rebuilds. Unlike the earlier 71 series that used dry liners, the 92 series surrounded its replaceable cylinder liners with coolant. This sounds like a minor change until you understand what it meant for mechanics. With wet liners, you could rebuild an 8V92 in a parking lot with basic hand tools. No machine shop required, no boring bars, no honing equipment, no precision measuring instruments beyond a good micrometer. The liners came pre-finished from Detroit, ready to drop in. Each liner had rubber O-rings that sealed against the block, keeping coolant where it belonged. When a cylinder wore out, you didn't resurface it. You threw it away and installed a new one. It was like changing a spark plug on a gas engine, except you were changing the entire cylinder. This design also meant better cooling. The coolant touched the cylinder liner directly instead of going through the block metal first. Heat transfer was immediate and efficient. In marine applications where engines ran at full power for hours, this made a huge difference in reliability. The wet liner system turned major engine overhauls into routine maintenance. Fleet operators loved it because downtime dropped dramatically. A good mechanic could change all 8 liners in a day. Try doing that with a conventional diesel that needs machine work. This accessibility helped cement the 8V92's reputation as the working man's diesel. Power ratings span from grocery getter to monster truck. The 8V92 came in more power configurations than any other Detroit engine. Base naturally aspirated version started at 360 horsepower. That's right, without any turbocharger at all, just the mandatory Roots blower, these engines made respectable power for moving city buses and delivery trucks. But Detroit didn't stop there. They kept adding boost until they reached the limit of what cast iron could handle. The 8V92T added a turbocharger for 430 horsepower. The TA version added an aftercooler, pushing output to 475 horsepower. The TTA went even further with sophisticated turbo controls, reaching 550 horsepower. But here's the shocking part. All these versions use the exact same base engine. Same block, same crank, same rods, same pistons. Detroit just kept adding air and fuel until they hit the mechanical limits. This modularity meant you could upgrade your engine as needs changed. Start with a naturally aspirated bus engine, add a turbo kit when you need more power, add an aftercooler when you need even more. It was like building with Legos, except each Lego weighed about 50 pounds and cost a month's salary. The military took this even further with experimental versions pushing 600 horsepower. These engines lived short, violent lives, but proved the 8V92 platform could handle almost anything if you were brave enough. The Silver 92 updates changed everything without changing anything. In the early 1980s, Detroit performed magic with the Silver 92 updates. They improved fuel economy by 10 to 14% without changing any major components. No new block design, no different displacement, no radical redesign. Just careful attention to details everyone else ignored. The updates focused on port timing, airflow dynamics, and injection timing. Detroit engineers spent thousands of hours with flow benches and dynamometers, tweaking tiny details. They changed the angle of the intake ports by a few degrees. They modified the exhaust valve timing by milliseconds. They reshaped the piston crown slightly. Each change by itself was almost imperceptible. Together, they transformed the engine. The Silver 92 updates proved that mature technology could still improve dramatically. While competitors were designing entirely new engines to meet tightening fuel economy standards, Detroit made their existing engine better through pure engineering refinement. Fleet operators who upgraded to Silver 92 specifications reported fuel savings that paid for the updates within a year. In an era when diesel fuel prices were skyrocketing, this was like finding money in your couch cushions. Except the couch weighed 2,000 pounds and screamed at 2,100 RPM. The Silver updates also reduced emissions without adding complicated equipment. By burning fuel more completely, the engines naturally produced less smoke and particulates. This bought Detroit precious time before emissions regulations forced more dramatic changes. DDEC electronics turned a mechanical monster into a computer. When Detroit diesel electronic controls arrived on the 8V92, it was like teaching an old dog to use an iPhone. This mechanical monster that had relied on springs, weights, and leverage for decades suddenly had a computer brain. DDEC didn't just control fuel injection, it revolutionized how these engines operated. The system monitored dozens of parameters hundreds of times per second: coolant temperature, oil pressure, boost pressure, engine speed, throttle position, ambient air temperature, and more. It adjusted injection timing on the fly for maximum power and efficiency. But here's what really shocked old-school mechanics. DDEC could diagnose itself. The computer stored fault codes that told you exactly what was wrong. No more guessing why an engine was down on power or smoking. The computer knew, and it would tell you if you asked nicely with the right diagnostic tool. DDEC also introduced something 8V92 operators had never experienced: consistency. Mechanical injection systems varied from engine to engine and changed as components wore. DDEC engines ran exactly the same from the day they were built until the day they were rebuilt. This consistency extended to governor control. Mechanical governors could hunt and surge, especially as they wore. DDEC held RPM rock steady regardless of load changes. For generators and marine applications where precise speed control mattered, this was revolutionary. The TTA's constant horsepower trick defied logic. The 8592 TTA introduced something called constant horsepower that made engineers scratch their heads. This engine maintained 365 horsepower at both 1950 and 2100 RPM. That's not how horsepower normally works. Usually horsepower rises with RPM until it peaks and falls off. But Detroit figured out how to make the TTA hold the same power across its entire operating range. They marketed this as Fuel Squeezer Plus technology. The trick involved sophisticated turbocharger controls and injection timing that adjusted based on engine speed. At lower RPM, the engine used more boost and advanced timing. At higher RPM, it reduced boost and retarded timing. The result was an absolutely flat power curve that delivered consistent performance regardless of engine speed. This mattered enormously for applications with variable speed requirements. A fire truck pumping water might run at idle, full throttle, or anywhere in between. With constant horsepower, operators got predictable performance at any speed. The same technology helped in marine applications where engines might cruise at 1600 RPM or run wide open at 2100. The TTA's constant horsepower also improved fuel economy in real-world use. Since the engine didn't have to rev higher to access its full power, operators could run at lower, more efficient speeds while still having all the power available when needed. It was like having your cake and eating it too, except the cake weighed a ton and could power a yacht. Fire departments created their own secret performance recipes. Fire departments across America developed underground performance modifications for the 8V92 that Detroit never officially sanctioned. These weren't just shade tree mechanics. They were professional engineers working with million-dollar equipment and lives on the line. They discovered combinations that Detroit's lawyers would never approve. Pierce Fire Apparatus became famous for their 450 to 475 horsepower 8V92TA packages. But behind closed doors, they were pushing 500 horsepower reliably. The secret involved careful matching of turbocharger specifications, custom aftercooler designs, and injection pump modifications that walked right up to the edge of what cast iron could handle. Some departments went even further. They experimented with water injection for cooling, propane injection for power, and even early nitrous systems. When you absolutely had to get a 30-ton ladder truck up a steep hill to save lives, emissions and warranty concerns took a back seat. These modifications spread through the fire service like wildfire. Departments shared notes at conventions, mechanics trained each other, and soon there was an entire underground network of 8V92 performance knowledge. Detroit knew about it but looked the other way. After all, these modifications proved how robust their basic design was. The fire service modifications eventually influenced Detroit's own development. Many improvements that showed up in later factory engines started as fire department experiments. It was real-world R&D at its finest, funded by taxpayers who just wanted their fire trucks to perform when it mattered most. Marine versions could run backwards on purpose. The Marine 8V92 came in both right-hand and left-hand rotation versions, and this wasn't just a simple matter of reversing the starter. Detroit actually built mirror image engines with different firing orders to make counter-rotation possible. This allowed boat builders to install twin engines that rotated in opposite directions, canceling out torque effects. In a twin-screw boat, having engines rotate in opposite directions eliminates the tendency to pull to one side. But here's what's wild. Detroit had to redesign significant portions of the engine to make this work. The camshaft profile was different because the valves had to open in a different sequence. The injection pump rotation was reversed. Even the blower drive had to be modified. The firing order changed from the standard 1-5-4-8-6-3-7 2 to 5-1-8-4-2-7-3, 6 for left-hand engines. This wasn't just running the numbers backward. It required careful engineering to maintain proper balance and smooth operation. Mechanics had to be extremely careful during rebuilds. Installing right-hand rotation parts in a left-hand engine would result in spectacular failure. Detroit color-coded components and stamped rotation directions everywhere, but mistakes still happened. The result was usually bent valves, holed pistons, or worse. Marine applications also pushed these engines harder than any other use. A yacht running offshore might operate at full power for hours, something unthinkable in truck applications. The wet liner design and massive cooling capacity of the 8V92 made this possible, but just barely. Jake brakes turned them into musical instruments. When Jacobs engine brakes were fitted to 8V92 engines, they created a sound that became the signature of American trucking. But the installation was far more complex than on four-stroke engines, and the results were dramatically different. The Jake brake on a two-stroke Detroit works by turning the engine into an air compressor. It opens the exhaust valves near top dead center, releasing compressed air instead of using it for power. But remember, the 8V92 already has a blower cramming air into the cylinders. Add Jake brake operation, and you're moving massive amounts of air through the engine. The sound produced was unlike anything else on the road. Where four-stroke Jakes produced a rapid-fire popping sound, the 8V92 created a continuous roar that could be heard for miles. It was so loud that many municipalities banned Jake brake use within city limits, specifically because of Detroit-powered trucks. The mechanical installation required precise adjustment. Too little clearance and the brake wouldn't engage properly. Too much and you'd damage the valve train. Detroit engines with both mechanical and DDEC controls could use Jake brakes, but the DDEC versions worked better. The computer could modulate brake application for smoother operation. Fire departments loved Jake brakes because they provided massive retardant power for heavy trucks on steep grades. When you're piloting a 70,000-pound ladder truck down a mountain, engine braking isn't a convenience. It's survival equipment. The Jake brake could provide up to 400 horsepower of braking force, saving service brakes from overheating. Have you ever heard an 8V92 with Jake brakes echoing off mountain walls? Let me know in the comments where you encountered these legendary engine brakes. They drank straight 40 weight oil. Like it was water, the 8V92 had an oil appetite that shocked operators coming from four-stroke engines. These engines specified straight SAE 40 weight oil in most applications, not multi-grade, not synthetic, just old-fashioned straight 40. And they consumed it at rates that would bankrupt modern engine owners. Detroit's official specifications allowed for oil consumption up to 1 gallon per 100 gallons of fuel burned. Think about that. A truck getting 5 miles per gallon could legitimately burn a gallon of oil every 500 miles. That wasn't considered excessive. It was normal. The two-stroke design was partly to blame. Oil had to lubricate the cylinder walls where the intake ports were located, and some inevitably got pulled into the combustion chamber. But Detroit engineers considered this a feature, not a bug. That oil burning provided upper cylinder lubrication that extended engine life. Fleet operators learned to buy oil in 55-gallon drums. They installed automatic oiling systems that continuously fed oil to the engine. Some long-haul trucks carried more spare oil than coolant. It was just part of operating a Detroit two-stroke. The straight 40 weight requirement came from the high operating temperatures and the need for oil that wouldn't break down under the constant punishment. Multi-grade oils of the era couldn't handle the heat and contamination. Synthetic oils were just appearing but cost more than the fuel, so operators stuck with dinosaur juice and kept pouring it in. In-frame overhauls made rebuilds a parking lot project. The 8V92's modular design made in-frame overhauls so easy that mechanics could rebuild engines without removing them from the vehicle. This wasn't just possible, it was routine. The wet liner system, combined with easy access to rod and main bearings, meant a complete rebuild could happen wherever the engine died. A skilled mechanic with the right tools could pull the cylinder head, extract the pistons and liners, install new components, and have the engine running again in 2 days. No engine hoist required, no trip to the machine shop, no waiting for parts to come back from specialized vendors. Everything needed was available from Detroit dealers in kit form. This capability transformed maintenance planning for fleet operators. Instead of scheduling trucks for week-long rebuilds, they could plan weekend overhauls. A bus could break down on Friday and be back in service Monday morning. The military particularly loved this feature. A broken engine in a combat zone couldn't always be extracted for rebuild, but soldiers could rebuild an 8V92 in the field with basic tools and replacement parts. Detroit even published military-specific manuals showing how to perform overhauls in austere conditions. The in-frame rebuild capability also made 8V92 engines economically attractive. While the initial purchase price was high, the ability to rebuild them repeatedly without major equipment made total life cycle costs competitive. Some engines went through 5 or 6 in-frame rebuilds over decades of service. The hot side aftercooler location broke every rule. Detroit mounted the aftercooler on 8V92 TA engines in the worst possible location, right between the turbocharger and the engine block in the hottest part of the engine bay. Every other manufacturer put aftercoolers in cool locations with fresh air. Detroit said, "Hold my beer," and stuck it in the inferno. The aftercooler used engine coolant to cool the compressed air, not ambient air like everyone else. This meant the intercooler could only cool the charge air down to coolant temperature, not ambient temperature. By conventional thinking, this should have resulted in less power and higher exhaust temperatures. But Detroit made it work through clever engineering. The water-cooled aftercooler was more consistent than air-to-air designs. It didn't care about ambient temperature or vehicle speed. Whether idling in Phoenix traffic or climbing Donner Pass in winter, the aftercooler performed the same. This consistency mattered more than maximum cooling capacity. The hot side location also shortened the intake path. Air went from turbo to aftercooler to engine in the shortest possible distance. This reduced turbo lag and improved throttle response. In stop-and-go applications like city buses and fire trucks, this made a huge difference in drivability. Maintenance was interesting too. The aftercooler core could be rotted out like a radiator when it clogged with oil and carbon. Try doing that with an air-to-air intercooler. The location that seemed stupid actually made service easier, proving once again that Detroit engineers thought differently than everyone else. Production ran 21 years. Without major changes from 1974 to 1995, Detroit built 8V92 engines with remarkable consistency. While competitors completely redesigned their engines every decade, Detroit just kept refining the same basic design. The last 8V92, built in '95, was fundamentally identical to the first one from '74. This consistency was both a blessing and a curse. Parts interchangeability was excellent. Many components would swap between engines decades apart. Mechanics trained on early engines could work on late ones without relearning everything. Fleet operators could stock one set of spare parts for engines purchased across 2 decades. But this consistency also meant the 8V92 never fully modernized. While competitors introduced 4-valve heads, electronic controls from the ground up, and advanced materials, Detroit kept building their traditional 2-stroke. They added DDEC electronics and improved various components, but the core design remained frozen in time. The end came not because the engine failed, but because emissions regulations finally caught up. The 2-stroke design simply couldn't meet the strict nitrogen oxide and particulate standards of the mid-90s without adding so much equipment that it lost its simplicity advantage. Detroit's Series 64-stroke replaced it, offering better emissions and fuel economy, but never matching the 8V92's personality. The 21-year production run proved that good engineering doesn't need constant revolution. Sometimes evolution is enough. The 8V92 served millions of miles in thousands of applications, screaming its way into diesel history. It's smaller than modern engines with half its power. Here's something that breaks modern minds. The 8V92 packs 736 cubic inches into a package roughly 44 to 48 inches long, 38 to 39 inches wide, and about the same height. Modern diesel engines making half the power are physically larger. How did Detroit accomplish this packaging miracle? Two-stroke architecture deserves the credit. Without a dedicated intake stroke, the engine could be shorter. The blower and turbocharger were tucked in close to the block rather than hanging off the side. The wet liner design eliminated thick cylinder walls. Every component was designed for minimum size and maximum strength. This compact size mattered enormously in real-world applications. Bus manufacturers could mount the engine under the floor without a huge bump. Marine installers could fit twin engines in hulls designed for one large engine. Military vehicles gained interior space for troops and equipment. The power density was extraordinary for the era. 550 horsepower from a package you could almost fit in a pickup truck bed was unheard of in the 70s and 80s. Modern engines need complex emissions equipment, 4-valve heads, and sophisticated cooling systems that add bulk. The 8V92 achieved its power through brute force and brilliant packaging. Weight was equally impressive at roughly 2,350 to 2,420 pounds dry. That's about half what a modern engine making similar power weighs. When every pound matters, like in marine or aircraft applications, the 8V92's diet paid dividends. Parts catalogs read like engineering textbooks. Detroit's parts catalogs for the 8V92 weren't just lists of numbers, they were complete engineering educations. Each section started with theory of operation, included cutaway drawings, and explained why components were designed specific ways. A mechanic could learn diesel engineering just by reading the parts book. This wasn't accidental. Detroit knew their engines would be maintained everywhere from professional shops to remote logging camps. They couldn't assume mechanics had formal training or access to technical schools. So they put the education right in the documentation everyone would have. The catalogs included troubleshooting charts that actually worked. Not generic, check the obvious suggestions, but specific diagnostic procedures based on symptoms. If your engine produced blue smoke at idle but not under load, the manual told you exactly which components to check in which order. They even included modification histories showing how parts evolved over time. If you had an early engine and needed to update it, the catalog showed which parts superseded which and why. This level of detail was unmatched in the industry. Some mechanics collected Detroit parts catalogs like technical libraries. A complete set covering all years and variations of the 8V92 could fill a bookshelf. But that bookshelf contained more practical diesel knowledge than most engineering textbooks. The catalogs became so respected that competitors' mechanics would reference them when working on non-Detroit engines. The diagnostic principles and engineering explanations applied universally. Detroit had inadvertently created the Diesel Mechanics Bible. Military versions broke every civilian rule. The military 8V92 engines threw civilian specifications out the window. These combat-rated engines ran on jet fuel, Arctic diesel, contaminated fuel, or basically anything flammable that could be pumped. They started in conditions that would kill civilian engines and ran at angles that should have caused immediate failure. Militarization started with hardened components. Pistons were forged instead of cast. Bearings used exotic materials. Gaskets were designed to survive nuclear, biological, and chemical decontamination procedures. Every rubber component had to resist military-specific fluids and extreme temperatures. The cooling system was overbuilt to handle desert operations. Military 8V92s could run at full power in 120-degree heat without overheating. They could also start at -40 without block heaters, though the procedure involved enough ether to knock out a horse. But the wildest modification was multi-fuel capability. Military engines had to run on whatever fuel was available in theater. The injection system was modified to handle everything from kerosene to heating oil. Power varied with fuel quality, but the engine would run. This flexibility saved lives when supply lines were cut. Some military versions pushed 600 horsepower for short durations. These engines lived fast and died young. But when you need to extract a damaged tank under fire, longevity takes a back seat to immediate power. The military rebuilt them frequently and considered engines consumable like ammunition. These combat experiences filtered back to civilian development. Improvements in durability, starting, and fuel flexibility pioneered by the military showed up in later civilian engines. War has always driven innovation, and the 8V92 was no exception. The two-stroke design was dead before it started. Here's the ultimate irony. When Detroit launched the 92 series in 1974, they already knew two-stroke diesels were doomed. Emissions regulations were tightening, fuel economy mattered more each year, and the fundamental characteristics of two-stroke engines worked against both trends. Yet they built it anyway and kept building for 21 years. Why would a company invest in technology they knew was obsolete? Because obsolete doesn't mean useless. The 8V92 filled needs that four-stroke engines couldn't match at the time. The power density, simplicity, and rebuildability made it perfect for specific applications despite its limitations. Detroit hedged their bets by developing four-stroke engines simultaneously. But they recognized that thousands of customers needed 8V92 capabilities and would keep needing them for decades. So they built the best two-stroke diesel possible, knowing it was the last of its kind. This decision proved brilliant. The 8V92 became the most successful two-stroke diesel ever built, powering everything from city buses to offshore race boats. It generated profits that funded development of the Series 64-stroke that eventually replaced it. The 8V92 was a technological dead end that refused to die. It kept improving, kept selling, and kept screaming right up until emissions regulations finally killed it. Even then, rebuilt engines soldier on 30 years later, proving that good engineering transcends technological fashion. The last Detroit two-stroke diesel turned out to be the best one ever built. That's all for today, folks. If you enjoyed this video, don't forget to subscribe and hit that like button so you don't miss the next one. See you there.